Hi, I'm Alexandre Brouste, a professor in statistics at Le Mans University, and I will talk about the one-step estimation procedure and its eponymic package, OneStep in R. This is a joint work with Christophe Duton. So in classical regular statistical experiment, the MLE, which is maximum likelihood estimator, presents nice asymptotic properties as the consistency and the efficiency. That means that it has the lowest variance between all kinds of estimation procedure. In general, this MLE has no closed form and must be approximated by some numerical methods as the gradient descent method on the likelihood function, which is quite time consuming, especially for the large data sets. In R, this procedure is proposed in some different packages like FitGIS+, estimation tools, distribution fit R. On the other hand, there is other estimation methods like the method of moments, which in specific statistical experiment is in a closed form, and then that can be computed faster. But this kind of estimation is not efficient asymptotically. So what we propose in the one-step package is to use the LeCam one-step estimation procedure that is both asymptotically efficient and also quite fastly computable. It works as is. You start with an initial guess estimation parameter, which is quite fastly computable, but not asymptotically efficient. And you correct it by a single step of the gradient descent method with the Fisher scoring method. So this allows to reach efficiency asymptotically. So in our package, OneStep, there is a single command, which is OneStep. You plug the sample in the data parameter, and you choose the character string for the dist parameter, which is the specific distribution for which you want to compute the estimation of the parameter. So there is several different distributions that are handled. The gamma, beta, chi-square, Cauchy, Weibel, negative binomial, and Pareto from the Acteur package, for instance. There is a single command, OneStep for the user. But inside, there is several internal procedure that taking into account the fact that there is a closed form for the initial guess estimation sequence, if the score and the Fisher information are explicit or have to be computed numerically. This can be, for instance, done on a simple example. Here you have a sample xn of independent and identically distributed gamma random variables with PDF is written here. And we want to estimate the parameter theta, which is the pair of the scale and shape parameter of this distribution. It is quite known that in setting, the MLE is not in a closed form and is quite time consuming to compute. But the score and the Fisher information matrix are explicit in this case and is related to the polygamma function. On the other hand, the moment estimator here is explicit and can be fastly computable, but it is not asymptotically efficient. So here we applied the one-step estimation procedure. You can see on the left that for a sample of size 100, and here 10,000 Monte Carlo simulation of the renormalized statistical error, the MLE, or the statistical error, reach the asymptotic efficiency, which is superposed here in red. For the moment estimator, which is in the middle, you can see that the asymptotic variance is bigger than the efficient red one. So it is fastly computable, but do not reach efficiency. With the one-step estimation procedure and a single step in the descent gradient method with Fisher scoring, you can see that you reach again efficiency. Here is the summary of the computation time. You can see that the one-step estimation procedure, which is of the same order as the moment estimator, is 40 times more fast than the computation of the MLE in this setting. And this performance ratio is constant with respect to the sample size. You can also use the init parameter in this function in order to use your own initial guess estimation procedure. Thank you for your attention. If you have any other question, please write to the email address. Here is the link of the package in the Crown site. And here's the reference of our paper that will appear in July in the Hard Journal.